Hey guys, in this particular video I'll be showing you yet another way you can calculate the equations of motion for a pendulum. Okay, in the previous videos I've shown you energy methods, but in this video I'm going to show you a way you can directly do it using the formula sum of torques is equal to your moment of inertia times by your angular acceleration. So here is your pendulum right here. We've got the length of our rope connecting to our point mass, which is L, and our point mass is of mass m. And we've defined theta to be equal to the angle measured from your vertical towards your rope at any time t. Okay, well, we know that there's a formula which can be useful here, which is the sum of torques around any point, let's call it point 0, is equal to your moment of inertia at that point times by your angular acceleration. Okay, so we can use this to calculate an equation involving theta. And to do that, we just need to create a free body diagram. So let's do that. Here's our free body diagram. We're going to have our point mass just here, and that's going to create a force due to gravity, which is going to be directly downwards, right? Not only that, but we're also going to have reactionary forces in both the x and y direction. This is going to be r, y, rx. And we also know that this right here is going to be our angle theta as well. Notice that I'm not including the force due to gravity on the rope. That's because I've assumed that the rope has negligible mass. And also notice that I'm not including the forces due to friction. That's because I've assumed that the friction forces are so small I can neglect them. Okay, so we could take our sum of torques around any point, but for simplicity, let's take them around this point. The pivot point. That way we don't have to include the torques. That way I don't have to include the torques from these forces R, Y, and Rx. So let's do that. We know there's only one force, and if you can imagine it, this force is really just a vector, and it's going to be going like that. And the torque done by that force is just going to be that force multiplied by your perpendicular distance. That shouldn't be anything new to us. And this perpendicular distance, what is that? Well, we know that this distance right here, if this is L, that means L sine theta, which is the same as that distance, so this is just going to be L sine theta as well. So in other words, we know there's only one torque which is going to be influencing, which is going to be in this term, and that's just going to be equal to minus mg L sine theta, and that's going to be equal to I0 alpha. And you may be asking yourself right now, why is there a negative sign out here? Why is there a negative sign out here? Well, that's because theta has been defined to be in the counterclockwise direction, and mg is trying to swing the system in the clockwise direction. So, in other words, because they're in different directions, mg L sine theta, the torque done by this force, is going to be negative. Okay, well let's continue this out. This is we can rewrite this now as minus mg L sine theta is equal to I0, your moment of inertia around your pivot point, times by alpha, or in other words, theta double dot. Theta double dot. Okay, well now this becomes a matter of calculating your moment of inertia. We've chosen to choose this point as our center of rotation, so let's see if we can figure out I0 from that. Remember, I0 is equal to your sum of r squared m. So for a set of discrete masses, this is your moment of inertia. And if we're concerning ourselves with your moment of inertia around point 0, that means that r, in this case, your length from your axis of rotation towards your mass, is going to be L in this case. So that's going to be L squared, and m in this case is just going to be m. Okay, not too much of a surprise. There's only one mass to consider, so we don't need to concern ourselves with any other terms at all because the mass of the rope is 0. Okay, so we can sub that in now, and we're left with minus mg L sine theta is equal to I0, which is L squared m, times by theta double dot. Alright, well let's see if we continue this even more. Let's make theta dot the subject of the equation, and we can write theta dot is equal to minus mg L sine theta all divided by L squared m. Okay, well, we're getting there. Let's see if we can simplify this a little bit more. Noticing that neither m nor L are 0, we can just cancel them from numerator and denominator, leaving us with the very familiar equation theta double dot is equal to minus g sine theta on L, or as written in previous videos, theta dot is equal to minus the ratio of g to L sine theta. That is our solution.